Recorded is rolling. It is Tuesday, January 21st. So you guys just turned in your rotational dynamics quiz. I'll be grading that soon. Back on Friday, I gave you guys a racquetball challenge. I did post the solutions to Google Classroom, but I want to flash them up here real fast, show you guys how to interpret those. Okay. I got I got this flyer in my mailbox this morning. It looked, I was looking at all the teachers' mailboxes. So this was in all teachers' mailbox because I didn't know for sure. So wait, is this like a science thing? It's just for science teachers. But so assuming there are teachers share this with you. This is a STEM career showcase. You guys know what STEM stands for? Science, technology, engineering, math. Science, technology, engineering, math. So this is, if you're interested in this is going to be on Thursday, January 30th. So what is that? 9 days from now. Right. So next week at 6 o'clock in the cafeteria. It says connect with UCF, Boeing, Brevard Zoo, Collins Aerospace, and more. All right, and we got there's some logos down here. All right, so that looks like a good opportunity. All right, there you go. Jot that in your planner if it can be helpful to you. All right, so I'm going to debrief with you guys AP Classroom Unit 5 today, and then you guys know I'm going to debrief Unit 6 tomorrow. Okay, so here for context, Unit 5. So AP's doing this new this year because last year they just threw rotational dynamics all into one unit. But this year, how they're breaking it up is they're doing rotational inertia and torque in Unit 5. Right? Yeah. So rotational inertia and then torque. Okay. And then Unit 6, they're allocating angular momentum and kinetic energy, well, rotational kinetic energy, right? So more like, right? So you guys good so far? All right. All right. So I did promise you guys going to debrief that racquetball challenge. So let's look at that. So here's the solution that I posted to Google Classroom after school, like on Friday. Right, here's what you guys did. There was an incline back there on the lab table. And I put, here it is. Here's the racquetball. So I put this racquetball up here at 200 centimeters was 200 centimeters, let it go. Right. And then you guys had to figure out where was it going to crash land. Right. So there were two parts to this. The first part was the ball rolls down the incline, which sort of had pretty well solved for you guys at one of the posters. Right? And the second part was you had to go back to projectile physics way back deep in last semester. Right. Figure out where's the ball going to land, right? Because we have some linear velocity in here, right? You guys see that, right? And then the projectile part itself, well, you have to consider that vertically that would constrain how much time it could fall for. And once you got the amount of time, which involved a quadratic equation, then you could switch over to horizontal motion and figure out where it's going to land. Right. So here's ball rolls down an incline. Here I solved this with conservation of energy, which is the easier of the two methods. The other method is you could go through torque, but that's a little harder. Right. So here I solved it for any I. You guys know where's let me find a rotational inertia table. I think I have it. Get it right. Oh no, I sure don't. Hang on. We gotta get this really fast. Rotational inertia. No, I must have it. Must have it right here. I just missed this. This rotational inertia table. Well, here it is. Something for. Okay. So, like, what is this racquetball? I think a hint I gave you guys was it's probably somewhere between these two, right? Okay. Like it's probably more like a basketball, like spherical shell, but it has a pretty thick skin. So maybe you could sort of interpolate which is. So what he did was they came up with a solution for each one of these. What would this be? What would this be? Where would the ball land? And it's probably going to be somewhere between those two. Okay. That's part of the fun of the challenge is you have to use a little creativity there. It's not exactly 100% straightforward. So I got it for any I. So here's what it is for like any ball rolling down with any rotational inertia comes out to that solution. Right. So it'll be something you should do. Right. Now, once you have that linear speed, that's a linear speed at the end. You guys see what's been solved for. It's that linear speed. That's how fast is it leaving at the end. Okay. But it's also, there's some angle going on here. And let me show you guys what I did with this angle. Because you guys may have taken a protractor and measured this angle directly. Did you guys get about 5 or 6 degrees? Something like that? Okay. All right. Now, what I did instead is, in the solution, my only measurements are, I got this H2, this height, this H1, the height of the lab table, and the length of the incline, which was 200 centimeters. Okay? If you know those and Earth gravity, I think that's all you need. Because you guys see this angle theta? like if you know H2 and you know L, isn't it locked in place what theta has to be, right? So you could also measure that, but sort of be redundant. And I want to show that you could solve it just in terms of H2, L, and H1. Okay, by the time we get to the end. All right, so once you got that speed, now what? All right, now we're going to switch over to projectile motion. So here's the height of the lab table. Okay, and oh look, it's the first kinematic equation. You can solve for t time, how much time it would take to fall at that point. Now the fact that it has some downward type motion, it follows through the kind of downish, okay, means that you can't use a simplified version. You have to use the full version, which means solving for t is going to lead to a quadratic equation. You guys know that? Okay, which looks like that. You guys know quadratic. Okay, so it comes out to this right here. Okay, all right, and this okay. Part of the quadratic here is how fast was it traveling initially in the vertical direction? Okay, well, let's see. Here's the full speed times sine theta. Okay, and the full speed comes from this rotational dynamics. Okay? And the sine theta you can actually get from H2 over L. Isn't that what sine theta is? Is H2 over L, right? Can I see it right there? Okay. All right. So that's going to lead you to getting the amount of time. Now, in terms of the measured values, it looks like this fun expression right here. So I can substitute this later. Okay, so that's how much time, right? For any Rayleigh ball. Notice it's in terms of generic I, right? So any Rayleigh ball. Right? All right, now going up to the end here. This one I had to fit landscape. It's the only way. All right, so it's really just this: how far the ball goes. It's how fast it's traveling in the horizontal direction, which is v cosine theta, and for how much time. Okay. Now, each one of these expressions has a whole story behind it. Here's this V that we got from the rotational dynamics, right? Conservation of energy. Okay. Now, cosine theta, if you go back way back to the beginning for the geometry, isn't that just this like the triangle divided by this L for the incline? Okay. And this side is, could you guys see the Pythagorean theorem? I want to make sure you guys see where this is coming from. Okay. Do you guys see that this leg of the triangle would be square root of L squared minus H2 squared? You guys see that? Right, if you do reverse Pythagorean. Okay. And then if you take that leg, which is the square root expression, and divide by the full length L, wouldn't that be the cosine relationship? Okay. I want you guys to see that that's exactly where this is coming from right here. You guys see that is cosine theta? Okay, you guys see that? That is cosine theta. Same thing. Okay. And then this t, okay, well, here's the result from that quadratic equation with it for the time, right? From that projectile. Okay. Hey, put it all together. Here's your either measured or known values. Okay. Oh, I told you guys the mass and radial size of the ball ends up canceling out, so it doesn't matter, right? As long as you know how the mass is distributed. Here's for a spherical shell, here's for a solid ball. So I tried each one. I got somewhere between 66 and 72 centimeters. And when I rolled it down myself, I got pretty much exactly that. I got about 67 centimeters somewhere there. So it aligned exactly with how it played out. Okay. All right, so there it is. There was your Friday challenge. Oh, here's the, well, got some notes set up. That's Friday challenge right there. All right, you guys ready to switch over to AP Classroom?